From the phone in your pocket to the complex avionics guiding a jet or, the intricate systems steering a deep-sea submersible, electronics are just everywhere.
Absolutely fundamental.
They really are. But have you ever stopped to think about what it truly takes to make these incredible devices survive, let alone function, in the most extreme environments on Earth and even beyond?
Yeah, we're talking conditions that would just obliterate most tech we use daily. Melt, freeze, crush.
Exactly. So today we're embarking on a truly fascinating deep dive.
We're looking into a foundational textbook, actually. Fundamentals of Design and Production Technology of Radioelectronic Means. It's quite a title, and it hails from Siberia.
Wow, okay.
And this isn't just about, wiring up a circuit board. Not at all. This gets into the meticulous, sometimes almost heroic engineering behind building resilience.
Resilience against what specifically?
It's everything. The biting cold of Antarctica, the relentless radiation of space. It's about survival engineering.
Okay, so our mission for this deep dive is to pull back the curtain. We want to unpack the foundational principles, the surprising details.
Yeah.
How these radioelectronic systems, RES we'll call them.
Yep, RES.
How they're conceived, designed, built, and crucially protected. How they function reliably under these, frankly, extraordinary conditions.
And just how complex the unseen engineering really is, it's going to change how you look at the devices around you.
I bet it will. All right, let's start unpacking this. So when we typically think about electronics, our minds often jump straight to the circuit board, maybe some wires,
Of course.
the visible stuff.
The tangible bits, yeah.
Mhm.
But this source, it starts much, much earlier. It begins with how these incredibly complex systems are even, categorized, how they're organized and broken down before a single component gets chosen.
Like the architecture before the bricks.
Precisely. It's about the structure first.
Mm.
And what's insightful is how it defines a radioelectronic system, an RES. It's not just the final thing you buy.
Right.
It's any manufactured item or set of items. And they make this key distinction between main production, that's what a company sells to customers.
The finished product.
Exactly. And auxiliary production. That's stuff the company builds for its own needs, like maybe specialized test gear or internal networks they use to make the main products.
Ah, okay. So that broadens the scope quite a bit.
It does. It helps us understand an RES can be anything from a tiny sensor to, an entire control system for a rocket.
I really caught my eye here and seems to simplify things massively is this modular principle. You mentioned Legos before.
Yeah, it's a bit like that, like super sophisticated Legos for electronics, but with intense precision.
Right.
The core idea is disaggregation. Fancy word, but it just means breaking down complex electronic schemes into smaller, functionally complete bits, sub-schemes or parts.
So you take a huge, complex system.
And you logically chop it up
Yeah.
into manageable, independent chunks.
Exactly. And the source details this modularity using a hierarchy. It follows a specific standard, GOST 2663285. GOST. That's a Russian standard, right?
Yes, it is. So at the highest level, you have what's called a radioelectronic module of the third level, REM-M3.
RAM3. Like what?
Could be a whole cabinet, a control panel, maybe a rack full of equipment, something functionally complete and interchangeable.
Okay, the big picture stuff.
Right. Below that, REM-M2, typically a block or a frame within that cabinet. Then you get REM-1, often a single printed circuit board or maybe a cell of components.
It's like a specific function board.
Usually, yeah. And finally, right at the bottom, REM-M0. These are the individual components, integrated circuits, resistors, capacitors, the discrete radio elements.
The actual building blocks.
So fundamental building blocks within REM-1. They don't have standalone use.
And this whole modular thing, why is it so critical?
Flexibility. It's huge for design, for manufacturing, and maybe most importantly, for maintenance and repair out in the field.
Repair.
Right. If a REM-1 module, that circuit board fails, you just swap it out. Pop in a new one. System's back online quickly. You're not replacing the entire, multi-million-dollar system.
Makes sense. Much more efficient. But how do you guarantee all these Legos, from the tiny REM-0 resistor up to the big REM-3 cabinet, actually fit and work and can be made the same way every time?
That's where standards and meticulous documentation come in. It's not just what you build, it's how you document every single aspect of
The
it.
paperwork trail.
More than just paperwork, it's the engineering language. The source highlights standards like ESKD, the Unified System for Design Documentation. Specifically, it mentions a 2.70184.
Okay, what's that cover?
It lays out the general requirements for execution of electronic schemes, how diagrams are drawn, the symbols used. everything.
So everyone's on the same page.
Exactly. It ensures interoperability, quality, consistency. An engineer anywhere, theoretically, can understand a design made elsewhere if they follow these standards. It's the common tongue.
And then there are these literatures, these single letters like O, O1, UABI. That seemed fascinating.
Oh, they are. They're not arbitrary at all. Think of them as a super precise tracking system for a product's documentation throughout its entire life.
A life cycle tracker.
Precisely. For instance, OPARO means the documentation is for an experimental prototype, just the first draft, basically.
Okay.
O1 means it's passed state acceptance tests, it's been rigorously vetted. U is for the pilot production run. A is after those tests.
Getting closer to prime time.
Right. B means it's finally greenlit for mass production. And I is for one-off or limited production runs.
Wow. So it's not just bureaucracy.
Not at all. It's a critical, built-in quality control system and lifecycle management. It ensures every change is documented, approved, tracked, from the first idea to full deployment. It's a roadmap of the product's maturity.
That's really detailed. Now, something else stood out, the role of the human designer. Even with all the computer-aided design, the CAD systems.
Yeah, the source makes a strong point here. Despite CAD becoming ubiquitous, the human designer's role isn't shrinking.
It's increasing. That seems counterintuitive.
It does, but think about it. Why? Because only humans can tackle truly novel, non-formal tasks.
Meaning problems CAD hasn't been programmed for.
Exactly. CAD is brilliant at optimization, running simulations, handling complex calculations quickly and accurately. But it can't invent a brand new solution to an unprecedented problem. It can't intuit a new design approach for, say, extreme conditions never encountered before.
So the creative leap.
Still rests firmly with human ingenuity. CAD handles the heavy lifting on calculations, but the spark, the innovative solution, especially for the really hard new stuff, that's human.
That's a powerful reminder, actually, even in our automated world. Okay, so we've got this meticulous planning, documentation, modularity. The foundation is laid, but now comes the really hard part. Making electronics that actually survive out there. Not in a nice, clean lab, but in the real, often brutal world.
Yeah, this is where the rubber meets the road, or maybe where the silicon meets the blizzard. Designing for climate and for sheer physical forces, these are massive challenges. They push engineering to its absolute limits.
So where do we start? What's normal?
Good question. The source defines normal climatic conditions as a baseline. Temperature around plus 25 degrees Celsius, plus or minus 10 degrees.
So room temperature, basically.
Pretty much. Relative humidity between 45 and 80%, and atmospheric pressure around standard sea level, roughly 8.3 to 10.6 times 10 to the 4 pascals. A comfortable indoor space?
But the Earth isn't exactly comfortable everywhere.
Far from it. The source divides the planet into 7 distinct climatic zones, and each one throws its own unique, often vicious set of challenges at electronic systems.
And we're not talking a little chilly or a bit warm. Let's paint a picture of these extremes. You mentioned Antarctica.
The very cold region, yes. Average minimum temperatures there are below minus 60 degrees Celsius.
The minus 60.
And the record low at Vostok Station, minus 88.3 degrees Celsius.
Unimaginable.
And it's not just the cold. It's often combined with powerful, biting winds that just suck the heat out of everything. Think about your smartphone trying to work there.
Forget it. The battery would die instantly. The screen would freeze.
Exactly. Just sending a text becomes an incredible engineering feat.
Yeah.
Then there's the general cold zone, large parts of Russia, Canada, Alaska, Greenland.
It's still pretty harsh.
Down to minus 50 Celsius. Annual temperature swings can be a staggering 80 degrees. Daily swings up to 40 degrees.
Wow.
And here's a weird one. The high atmospheric transparency in these regions actually promotes air ionization. That leads to static electricity building up on equipment.
Static. Like a shock.
Yeah, potentially damaging levels of static discharge. Plus, you've got constant threats from icing, hoarfrost, and fine snow dust getting into every nook and cranny.
Okay, let's go the other way. Hot and humid.
The humid tropical zone, near the equator, Central and South America, parts of Africa, India, Southeast Asia. Temperatures are milder, maybe 20-25 Celsius on average.
Sounds pleasant.
But the humidity is extreme, often combined with high salt concentrations, especially near coasts. This makes the atmosphere incredibly corrosive. Metals just rust away.
Salt spray, yeah.
And get this, these conditions are absolutely perfect for mold growth. Over 10,000 species of mold thrive there.
Mold. On electronics.
Yes, mold can literally grow on and eat away at electronic components and insulation materials. It can cause short circuits, complete system failure. It's a biological attack.
That's wild. Okay, what about hot and dry?
Dry tropical, think North Africa, Central Australia, parts of the Arabian Peninsula. Temperatures can soar up to plus 55 Celsius. Humidity is very low.
So baking hot.
Baking hot and intense solar radiation up to 1,500 watts per square meter. That heat load is immense, but the silent killer here is often the dust and sand.
Abrasive.
Highly abrasive. It literally sands down components, wears away coatings, and the dust itself can be chemically active, causing chemical wear too. It's a relentless physical and chemical assault.
So humidity is clearly a major villain here. It's not just water.
No, it's insidious. Humidity leads directly to metal corrosion. It causes aging and degradation of non-metallic materials like plastics and rubbers. And critically, it changes the electrical properties of insulators. They stop insulating as well.
Leakage currents.
Exactly. And making it worse, atmospheric water is rarely pure H2O. It's often contaminated with active substances, carbonates, sulfates, chlorides from sea spray, industrial gases like sulfur dioxide. These act like catalysts, speeding up corrosion dramatically.
A chemical soup attacking the electronics.
Pretty much. And it's not just climate at ground level. Pressure and altitude are huge factors too.
Right, for planes, satellites.
The source points out how pressure drops significantly with height. At 16 kilometers up, near the edge of the troposphere, pressure is only about a tenth of sea level pressure.
How does that affect things?
Lower pressure means less air for cooling through convection. It also reduces the dielectric strength of air, the voltage it can withstand before an arc jumps across, so you need wider spacing between high voltage components.
Okay, and temperature varies wildly up there too, right?
Incredibly complex variations. Temperature drops in the troposphere, then increases in the stratosphere, drops again in the mesosphere, and then skyrockets in the thermosphere, potentially reaching over 700 degrees Celsius.
Wow. So aerospace engineers have to account for this huge range.
Absolutely. And remember those active substances. They vary by location, too. Coastal areas are way more corrosive due to salt chlorides compared to inland areas.
It's a multi-dimensional problem. Climate, pressure, altitude, location.
And we haven't even gotten to the physical abuse yet. Mechanical impacts.
Like launching a rocket or driving a tank.
Exactly. These aren't gentle forces. The source outlines several types. There's shock, a rapid, sudden change in acceleration, defined by its peak acceleration, duration, and how many times it hits.
A sharp jolt.
Right. Then linear acceleration. That's what equipment feels when a vehicle speeds up, slows down, or turns. Think about being pushed back in your seat. Electronics feel that too, but sometimes much more intensely.
Like in a rocket.
For sure. Small, solid fuel rockets can subject their electronics to forces up to 50 G, 50 times the force of gravity.
Incredible. What else?
Acoustic noise. The intense sound from engines, rockets, planes, ships, even heavy machinery.
Noise can physically damage things.
It can mechanically load all components inside. The sound waves cause vibrations, flexing, stress. It's a non-contact mechanical assault, especially on lighter parts.
So all these environmental factors, temperature, humidity, pressure, shock, vibration, noise. What's the bottom line for the device?
They directly impact the critical reliability indicators, things like mean time to failure, MTTF, or mean time between failures, MTBF. Basically, how long can you expect it to work without breaking?
And engineers have to design for specific levels.
Absolutely. The source mentions practical impacts like needing specific insulation resistance values depending on the climate. Humid environments demand much higher resistance. Packaging needs to withstand multiple shocks like that 147 millifarad jolt for 10-15 milliseconds we talked about.
And this isn't just for military or space gear.
No, even household electronics have standards. The source mentions GEM OST standards for operation and safety. Your toaster has to survive being dropped within reason and handle typical home humidity levels. The principles apply across the board, just with different severity levels.
Okay, so we've set the stage with these incredibly harsh environments. Now, let's zoom in. How do engineers actually get signals and power moving reliably through these systems, even when they're being shaken, baked, or frozen?
This is where we get into the literal nervous system of the device, the communication lines, the electrical connections.
Wires and traces.
Right. The source defines these broadly as lines of transmission, LPs, and contacts. And there's a key distinction between signal LPs carrying information and power LPs delivering energy.
Both need a return path. Right.
Critically, yes. Both need a ground or zero potential line for return currents. And getting that ground path right, keeping it clean, low impedance, is often one of the biggest challenges for signal integrity and noise suppression. A bad ground invites problems.
It's not just one kind of wire either, is it?
Oh no. The source describes different constructions. You might see rectangular bare wire in some specific power applications. More commonly, multi-stranded, round insulated wire.
The stuff we usually see.
Yeah. And engineers don't just run individual wires everywhere, especially in complex systems. That'd be a nightmare for assembly.
A rat's nest.
Exactly. So they bundle lines into constructive technological units, things like harnesses looms of wires tied together or flat ribbon cables. It makes assembly much more efficient and less prone to errors, like connecting wire A to pin Z by mistake.
Makes sense. But what about the signals themselves, especially faster ones?
Signal integrity. That's a huge field. At higher frequencies, wires stop behaving like simple conductors. They become long lines, exhibiting transmission line effects.
Meaning the length matters a lot.
Yes, and the geometry. The source discusses different forms: microstrip and strip line conductors printed directly onto circuit boards, twisted pairs, flat cables, coaxial cables. Each has specific electrical characteristics, impedance, loss, suited for different jobs.
You mentioned high frequencies. There's something called the skin effect, right?
Or surface effect, yeah. It's fascinating. High-frequency currents don't flow uniformly through the whole conductor cross-section. They tend to concentrate near the surface, the skin.
Why is that a problem?
It effectively reduces the available area for the current, which increases the conductor's resistance at those high frequencies. This higher resistance causes signal loss, attenuation, and distortion, especially for sharp digital pulses which contain many high frequencies.
So how do engineers fight that?
One common way is using Litz wires made of many thin, individually insulated strands, all twisted or woven together. This forces the current to distribute more evenly across the many surfaces, reducing the effective resistance compared to a solid wire of the same overall size.
Clever. Like maximizing the surface area internally.
Sort of, yeah. It mitigates the skin effect,
Yeah.
and this all points to the critical role of shielding
Protecting the signals from outside noise.
and preventing them from leaking out and interfering with other things. Using LPs with a metallic shield, properly grounded, is incredibly effective. The source explains that grounding the shield breaks the parasitic capacitive coupling between the central signal conductor and external noise sources.
Okay, capacitive coupling is like signals jumping across an air gap.
Essentially, yes.
Yeah.
Like tiny invisible capacitors forming between wires. Shielding intercepts that. It's absolutely key for reducing crosstalk signals bleeding between adjacent lines and minimizing susceptibility to external interference. Without good shielding and grounding, your perfect circuit design could be completely overwhelmed by noise.
And the insulation on the wire itself is important too.
Vital. Material and construction have to provide high dielectric strength, withstand high voltage without breaking down, and high insulation resistance, meaning very little current leaks through it.
Even under tough conditions.
Especially under tough conditions. High humidity, extreme temperatures, long-term storage. The insulation has to hold up and prevent shorts or signal leakage. Signals need to stay where they belong.
This brings us to the heart of modern electronics. The printed circuit board, the PCB.
Indeed. And the source particularly highlights multi-layer PCBs, or MPPs. They offer huge advantages.
Like fitting more stuff in.
That's a big one. High commutation properties, meaning you can route many complex signals in a small space. Connections between layers are made using metallized through-holes.
Drilled and plated tunnels.
Exactly. This allows much higher component mounting density, and crucially, it enables shorter connection paths between components. Shorter paths are essential for high-frequency operation, less delay, less signal degradation.
Wow.
MPPs allow for internal layers dedicated to power distribution or, importantly, ground planes. These act as built-in shields, improving electrical characteristics, reducing noise, and they also help spread heat, acting as heat sinks. It's a truly 3D approach to circuit layout.
So designing one of these, it must be complex. How do they figure out the size?
The source mentions calculating the approximate PCB area based on the total mounting area needed for components, plus a filling coefficient, basically, how densely you pack things, usually between 0.4 and 0.85. They also follow standards, often recommending simple rectangular shapes, max aspect ratio 5.1 for manufacturability.
And stiffness matters too. especially if it's going to vibrate.
Absolutely. PCB stiffness is calculated using material properties like Young's modulus, how stiff the material is, its thickness, and Poisson's ratio, which
Yeah.
relates sideways deformation to axial deformation. Glass fiber laminate is common, but you might use metal core PCBs for better stiffness or heat spreading.
Material selection is key then.
Crucial. Chosen based on mechanical strength, water absorption, you want low. Dielectric properties, how well it insulates, and adhesion, making sure the copper traces stick properly. The source even mentions flexible PCBs.
Flex circuits, they seem useful.
They can be great for connecting different boards or fitting into tight, awkward spaces. The source says they can reduce inter-cell connection complexity by 15–25%, but there's often a trade-off.
Reliability.
Potentially, yes. The source note's failure rates can be 1 to 4 times higher than fixed connections in some cases. It's always a balance, flexibility versus robustness.
And placing the components on the board.
Hmm.
That's not random, I assume.
Far from it. It's a strategic process. You break the schematic into functional blocks, choose compatible IC families, standardize connectors, minimize wire lengths, avoid running sensitive signal lines parallel to noisy power lines to reduce coupling.
Dealing with those long line effects.
Exactly. Careful routing is needed. And managing heat is critical, placing heavy components or hot components near mounting points or heat sinks, ensuring good airflow paths. Every placement decision impacts performance and reliability.
And the precision needed for manufacturing must be tiny.
Incredible precision. The source refers to strict tolerances for conductor width, spacing, hole positions, down to fractions of a millimeter. Consistency is key for electrical performance.
You mentioned heat and PCBs. How hot can components typically get?
The source suggests a typical maximum operating temp for many components is around 75–85 degrees C. But how easily heat escapes depends hugely on the PCB material itself, its thermal resistance.
Lower resistance is better.
Yes, means heat flows away more easily. Standard glass epoxy might have a thermal resistance of, say, 26 degrees C per watt. A flexible PCB on a steel base could be as low as 8 degrees CW, much better heat dissipation. This choice can literally make or break a component's lifespan.
Okay, wires, PCBs.
Go
What
on.
about the next step? Fiber optics.
Right. The present and future for many high bandwidth or sensitive applications. Fiber optics offer fundamental advantages.
Like?
Significantly reduced volume and mass compared to copper cables, huge for aerospace, greatly increased radiation resistance, and crucially, total elimination of electromagnetic crosstalk and interference.
Because it's light, not electricity.
Exactly. Light signals don't generate EM fields in the same way. The basic structure is a core, where light travels, surrounded by cladding with a different refractive index to trap the light via total internal reflection. Multiple fibers can be bundled in a protective sheath.
So ideal for noisy environments or where data security is paramount?
Precisely. High bandwidth, reliable, electromagnetically silent.
We keep using the word reliability, but what does that truly mean when you're talking about an electronic system, especially one designed for these tough environments? It sounds like it's more than just it works.
Oh, much more. Reliability, as the source unpacks it, is a really comprehensive term. It includes several aspects. Workability, does it do its job? Durability, how long does it last before wearing out?
Right.
Failure-free operation, what's the probability it won't fail in a given time? Maintainability, how easy is it to fix? And recoverability, can it be restored after a failure?
So it covers the whole life cycle.
Exactly. The source also defines the resource of a product, its total operational lifetime, up to a limit set by the technical documentation. It's a holistic view.
Now, you mentioned failure-free operation. There was a really surprising statistic in the source about mean time to failure, MTTF or TORA.
Ah, yes, the 1,000-hour example. It's a classic misconception.
So a device with an MTTF of 1,000 hours, it doesn't mean it's likely to work for 1,000 hours.
Not for a single device, no. Especially if failures follow an exponential distribution, which is common for sudden, random failures. For that 1,000-hour MTTF device, the probability of it working without failure for the first 10 hours is only 99%.
Only 10 hours for 99%.
Wow. And after 100 hours, maybe 90% are still working. After the full 1,000 hours, the MTTF point, statistically, only about 37% would still be operating.
So MTTF is really an average across a large population.
Precisely. It tells you the average lifespan, but says little about the probability of any one unit surviving that long. It highlights the deeply statistical, probabilistic nature of reliability. It's sobering for engineers designing critical systems.
How do they visualize this over time?
Often with the bathtub curve, it's a classic representation. It shows failure rate versus time.
Why a bathtub?
because it often looks like one in cross-section. High failure rate initially, that's infant mortality, manufacturing defects weeding themselves out. Then a long flat bottom, the useful life period, where the failure rate is low and relatively constant, dominated by random failures. And finally, the curve slopes up again, the wear-out phase, as components age and degrade.
And there are different mathematical models for these phases.
Yes, engineers use different probability distributions. The exponential law is often used for that flat, random failure period. The normal or Gaussian law often applies to wear-out failures. The Weibull law is versatile, often used for electromechanical parts. The Erlang law for repairable items. And the Poisson distribution can model the number of failures in a given time for repairable systems. Each model captures different failure behaviors.
So, given that failures will happen and perfection is impossible, how do engineers actually build in reliability?
Especially for critical systems.
It starts with the structure itself, how the components are interconnected. This is called structural reliability.
Okay, how does the connection method affect things? Dramatically. The source contrasts the main types. Series connection. Think Christmas tree lights, where if one bulb goes, the whole string dies. All elements must work. The overall system reliability is the product of individual reliabilities. It drops fast as you add more parts.
Not great for critical systems.
Generally not on its own. Then you have parallel connection. This is a huge leap. The system only fails if all the parallel elements fail. The probability of success is much higher, calculated as 1 minus the product of the individual failure probabilities.
So you have backups built in.
Exactly. It provides redundancy. And most complex systems use mixed connections, combinations of series and parallel paths, carefully designed to balance reliability, cost, and complexity.
Which leads to the big question. If components aren't perfect, how do you get maximum practical reliability when failure just isn't an option?
There are several key strategies. First, fundamentally eliminate errors at the source. Minimize design flaws, manufacturing defects, operational mistakes, quality control from day one.
Makes sense.
Second, using new, inherently more reliable components has driven huge gains historically. The source points to integrated circuits, ICs, significantly boosting reliability in third and fourth generation electronics compared to older discrete components.
Fewer parts, fewer connections to fail.
Right. But even the best components have a non-zero failure rate. So the most powerful structural technique is redundancy. Duplicating critical parts or systems.
Providing a backup.
Yes, and this is where the math gets compelling. The source gives this fantastic example. If a single module has a reliability of 0.7, a 70% chance of working for a given time.
Okay.
Adding just one identical redundant module in parallel boosts the system reliability to 0.91.
Wow, from 70% to 91% just by adding one backup.
And adding two redundant modules takes it to 0.973. It shows the exponential power of redundancy. It's like buying reliability insurance, structurally.
Are there different ways to implement redundancy?
Yes. General redundancy means duplicating entire modules or subsystems. Element-by-element redundancy duplicates individual ICs or even single components.
Which is better?
Element-by-element is often more effective in boosting reliability for the same number of added components, but it requires many more interconnections, adding complexity and potential new failure points in the connections themselves. It's a trade-off.
And what about systems that need to actively choose the correct output if one part fails?
That's where majority elements or voting systems come in, like 2 out of 3, 3 out of 5, even 4 out of 7. The system takes the output from the majority of redundant channels. If one channel gives a faulty reading, the others outvote it.
So the system self-corrects, in a way.
Exactly. Essential for things like flight control systems or critical safety interlocks where continuous, correct operation is absolutely paramount.
Okay, we've got reliable circuits, maybe with redundancy built in.
Yeah.
But how do you physically protect this delicate stuff from those brutal environments we talked about earlier, the moisture, the salt, the dust, the temperature extremes?
It comes down to the outer shell, the physical defenses. Strategic engineering of coatings, seals, and thermal management. These are just as vital as the circuits inside.
Let's start with coatings. What are they for?
Primarily, safeguarding parts from corrosion, aging, drying out, decay. The source classifies them into purely protective, decorative, where looks matter too, and special coatings.
Special like what?
Maybe for radiation shielding, surviving deep cold, or resisting biological growth like that mold we mentioned.
What are they made of? Common materials.
Things like nickel, copper, zinc, tin, silver are common plating materials. Often multi-layer coatings are used, maybe just 1 to 15 micrometers thick in total. Each layer might provide a different benefit, like a base layer for adhesion, an intermediate layer for corrosion resistance, and a top layer for wear or appearance.
Now are they applied?
Various processes. Oxidation forms an oxide film, often on steel or aluminum. Looks decent, gives some corrosion resistance, but it can be porous and not very tough, often used as a primer before painting.
Okay.
Anodizing is an electrochemical process mainly for aluminum. It creates a really hard, stable, highly insulating, corrosion-resistant film. It can even be dyed different colors.
Like on some phone casings.
Exactly. Then there's phosphating, typically on steel. Forms a protective film with good anti-corrosion properties, electrical insulation, and good paint adhesion. But again, can be porous and not super strong, so often a primer. And of course, paint and varnish. Good corrosion protection, but limited mechanical strength and heat resistance. You often see multi-layer painting for better quality, and different varnishes are chosen for specific resistances: water, oil, chemicals. It's a whole science of surface engineering.
So that handles surface protection. How do you keep stuff out? Water, dust.
Sealing,
Yeah.
creating a barrier. A common method is using elastic gaskets, like rubber or silicone seals, compressed between, say, a lid and a casing.
How much compression?
The sweet spot is usually 25–30% of the gasket's original height. Too little, it doesn't seal. Too much, and it ages rapidly and fails. Precision assembly matters. Simple rectangular gaskets are easy, give air tightness, but might not stop water vapor diffusion over time, which is tricky in humid places.
What about really tough environments? Vacuum, high pressure, high temp?
For those extremes, organic materials like rubber are often forbidden. They can outgas release vapors that contaminate sensitive systems or simply degrade. So engineers have to use metals, ceramics, or glass seals. Much harder to implement, but necessary.
You mentioned moisture traps before.
Yes, porosity in materials, especially cast metal parts or some plastics, can act like tiny sponges, collecting moisture, dirt, grease over time. This trapped stuff can then slowly migrate into the sealed volume.
How do you stop that?
One way is epoxy impregnation under vacuum, forcing resin into the pores to seal them off. For really critical applications, they place desiccants inside the enclosure.
Like those little silica gel packets.
Exactly, but often more potent ones like calcium chloride or phosphoric anhydride. They actively absorb any moisture that gets in or out gases from internal components, keeping the internal humidity below 80%, ideally.
And for the ultimate seal.
Metal gaskets. Copper or stainless steel, often coated with softer metals like aluminum or indium that can deform to create the seal. But these require huge compression forces. The source mentions 20–30 kilograms per centimeter of gasket length. That's serious clamping force needed.
Wow. Okay, coatings, seals. Now, the big one, heat. Thermal management, modern electronics get hot.
They really do. More power packed into smaller spaces means more heat to get rid of. And as we discussed, the external temperatures can be extreme, from Antarctic cold, -88°C, to direct sun, +90°C on Earth, and even wider swings in space, -150°C to +300°. It's a massive challenge.
So thermal analysis is step one, finding the hot spots.
Absolutely crucial. Identify the critical components prone to overheating. Then select the right thermal management system, as the source calls it. It's not one size fits all.
What are the options?
The simplest is natural convection, letting hot air rise. Works for low power densities. For more heat, forced convection, using fans to actively move air.
Standard stuff. What about higher power?
You might move to water-air cooling. Combines liquid coolant loops with airflow. Offers multiple heat paths away from the components. Can even be used inside sealed racks.
Keeping things stable is key too, right? Not just cool.
Yes, thermostatic control. Can be passive, using insulation or thermal dampers to slow heat transfer, or active, using heaters to keep components warm in extreme cold, or maintain a very stable temperature. Material choice matters: copper for high precision, aluminum for less critical stuff.
Now, there was a really cool one for space. Screen vacuum insulation.
Ah, yes, SVTI. Fascinating stuff. Used in space or for things like Dewar flasks, thermoses. It's layers of thin reflective material like aluminum foil, just 5–15 microns thick, alternated with insulating layers like glass, paper, or mylar, all under vacuum.
How does that work?
The vacuum stops conduction and convection. The multiple reflective layers drastically reduce heat transfer by radiation. It's incredibly effective insulation. The best 60-layer structures can have astonishingly low thermal conductivity. Sometimes they even use gold plating for better radiation properties.
Amazing. And heat pipes, they sound clever too.
Heat pipes are fantastic, highly effective passive devices. They transfer heat using phase change. A working fluid inside evaporates at the hot end, travels as vapor to the cold end, condenses, releasing heat, and then returns as liquid via a wick structure.
Like a circulatory system for heat.
Exactly. And they can work over huge temperature ranges depending on the fluid, from near absolute zero up to almost 800 degrees C. Very efficient heat movers.
What else? Radiation?
Radiation cooling is only really effective in vacuum, like space. Heat radiates away as electromagnetic waves. It's proportional to the fourth power of temperature. Important in space, but often negligible on Earth if other cooling methods are present. And there's thermoelectric cooling, the Peltier effect, using semiconductor junctions to pump heat, creating a cold side and a hot side. Good for localized cooling, but efficiency can be a challenge.
So the goal is always to maintain a stable internal temperature, like 25 degrees C.
That's the ideal normal thermal regime. And here's that critical takeaway again. The source states that for every 10 degrees C deviation from this optimal range, up or down, the equipment's lifespan is roughly halved.
Halved? That's huge.
It really underscores why thermal management is so vital and why engineers put so much effort into it. Keeping things in that narrow optimal window directly translates to longevity and reliability.
We've covered the environment, launch, climate, heat, seals. But what about just physical abuse?
Yeah.
Shocks, vibrations, like that rocket launch you mentioned, or a Jeep bouncing over rough terrain. How do you build electronics tough enough for that?
This is all about mechanical robustness, designing the structure to withstand physical forces. First, we need to define the mechanical loads.
Okay, what are they?
We touched on them earlier. Linear accelerations from changing speed or direction. Shock, that sudden, sharp change in acceleration, defined by its peak value, duration, pulse shape. Vibration oscillatory motion, described by amplitude and frequency. Engineers quantify these using overload coefficients, often in multiples of g, the acceleration due to gravity. And noise, too.
Yes, acoustic noise, translating into mechanical stress, especially on lighter, larger surface area components. It makes things vibrate.
Which brings us to resonance. That sounds dangerous.
It can be. Resonance happens when the frequency of an external vibration matches a structure's own natural frequency, the frequency it wants to vibrate at. When that happens, the deformations, the bending and flexing can become maximal, potentially leading to catastrophic failure, like an opera singer shattering glass.
So engineers have to avoid it at all costs.
They absolutely aim to.
Yeah.
The goal is to design the structure so its natural frequencies are well outside the range of expected operational vibrations. If the environment vibrates at 100 hertz, you don't want your circuit board having a natural frequency near 100 hertz. This is a fundamental challenge in structural design.
How do they figure that out?
They model the structure as an oscillating system. It has mass, stiffness, how much it resists bending and damping, how it dissipates vibrational energy like friction.
The forces acting on it. Right. There are the exciting forces, the external vibrations, restoring forces like springiness, pulling it back to shape, damping forces, resisting motion, turning vibration into heat, and inertial forces related to mass and acceleration, resisting changes in motion. Understanding this interplay is key.
So they do calculations, strength calculation.
Yes. Often complex parts like PCBs or housing walls are simplified into models, beams, plates, frames to calculate stress, internal forces, and strain, deformation, under expected loads.
And there are clever ways to make things stronger without adding much weight.
Definitely. The source has this fantastic example about stiffness enhancement. Take a simple flat beam. Now, add a small vertical rib along its length. This can increase the beam's stiffness, its resistance to bending, by about 20 times.
20 times.
While only increasing the material used by maybe 25%. It shows how smart structural geometry can provide huge gains in robustness with minimal weight penalty. It's elegant engineering.
How do they protect the whole unit from external vibrations, like mounting it in a vehicle?
That's vibration isolation. Using elastic supports, often called amortizers or vibration isolators, between the electronic unit, the RES, and its base.
Like shock absorbers.
Exactly like that principle. These isolators act like springs and dampers. They form an oscillating system designed to absorb vibrational energy and act as a low-pass filter, stopping high-frequency, damaging vibrations from reaching the sensitive electronics inside.
Are these just rubber mounts?
They can be, but often they're more sophisticated, precisely engineered components. The source mentions various types with specific parameters, resonant frequency, load range, damping coefficients. They are chosen carefully based on the expected vibration environment and the weight of the equipment.
What are the key design rules for using them?
Keep the center of gravity stable. Use standardized vibration isolating bases where possible. Crucially, ensure internal connections like flat cables or grounding buses are also stable and won't fatigue or break due to the relative motion allowed by the isolators. Even the maximum unsupported length of bare wires needs calculation to prevent them resonating.
Wow, down to the wire level. It's meticulous.
It has to be. And underpinning all of this is material properties for strength, choosing the right materials.
Especially for things like spacecraft, where weight is everything.
Absolutely critical. The source gives that Saturn V example. Saving 1 kilogram of payload could save 42 kilograms of fuel. That drives an intense search for materials with high specific strength and specific stiffness, the strength or stiffness you get per unit of density. Maximum bang for the buck, weight-wise.
What kind of materials are we talking about?
Various steels, aluminum alloys, magnesium alloys, copper, titanium alloys are common metals. Also non-metals like phenoplasts, glass-reinforced plastics like fiberglass composites, Gedinax, each has different tensile strength, yield strength, stiffness, Young's modulus, often tunable with heat treatment or alloying.
And how do you make them last longer under repeated stress, like vibration? Fatigue strength.
Several techniques. Surface hardening, making the outer layer harder. Thermochemical treatments. Shot peening, blasting the surface with small beads to create compressive stress, which resists crack formation. And ensuring smooth transitions between surfaces, avoiding sharp corners where stress concentrates and cracks can start. Building for endurance.
Okay, physical impacts, climate,
Ow.
done. But electronics face invisible threats too, right? Electromagnetic interference, radiation.
Yeah.
This sounds like the real invisible battlefield.
It truly is. Let's start with electromagnetic compatibility, or EMC. This is all about making sure devices don't mess each other up electronically and can function properly in their intended electromagnetic environment.
What causes problems?
Lots of things. Signal distortion is one. It can happen due to line discontinuities. That means sudden changes in the electrical path.
Like,
Mismatched impedance resistance to AC signals at the start or end of a line. Switching from a wire to a PCB trace, which have different characteristics. Even just manufacturing variations, or branching a signal line to multiple destinations.
and these cause reflections.
Exactly. You get a reflection coefficient, a measure of how much signal energy bounces back from the discontinuity instead of going forward. This messes up the signal shape, especially for digital data.
What else? Signals jumping between lines.
Yes, parasitic coupling, unwanted signal transfer, can be capacitive coupling through stray capacitance between conductors, like tiny antennas talking to each other. Can be inductive coupling due to mutual inductance, especially when wires run parallel, acting like tiny transformers. Or conductive coupling when different circuits share a common resistance, often in the ground path, creating ground loops that inject noise.
And power supplies themselves can be noisy.
Oh yeah, power supply noise, ripples, spikes is a constant headache. The source mentions using RC filters, resistor capacitor networks, and strategically placed parallel capacitors, often a big electrolytic one for low frequencies, and a small ceramic one for high frequencies, right near the ICs to smooth out the power and provide clean voltage, like tiny reservoirs of clean power.
This sounds like grounding is super important again.
Absolutely critical. The source stresses using separate ground buses or planes for different circuit types, low signal analog, digital, high power, to prevent noise from coupling between them via the ground path. And how you connect to ground matters. Monolithic connections, soldered or welded, are far better, lower resistance, and more reliable than clamped or screwed connections for grounding. You need a pristine, low impedance path back to the reference potential.
So how do you defend against all this interference?
Shielding is the primary defense. Blocking electromagnetic fields, different types exist. Electrostatic shielding uses a grounded metal screen to intercept electric fields, basically shorting out that parasitic capacitance. But its effectiveness depends heavily on a good, low-inductance ground connection for the shield itself.
Okay, what about magnetic fields?
For low frequencies, magnetostatic shielding uses materials with high magnetic permeability, ferromagnetic materials like mu metal, to divert the magnetic field lines around the sensitive circuitry, like creating a preferred path for the field to follow away from your components.
And for higher frequencies?
Electromagnetic shielding combines both principles, using conductive materials to reflect and absorb electromagnetic waves. Shielding effectiveness generally increases with frequency, and the source notes that even thin metal foil can be surprisingly effective above 10 megahertz.
Are there specific ways to shield wires?
Yes. The source shows various schemes using shielded twisted pairs, different ways of grounding the shield, At one end, both ends, depending on the frequency and type of interference. It's a complex optimization to get the best noise suppression.
Okay, EMC is one invisible threat. What about the other really big one? Radiation.
Ah, yes, radiation effects. Particularly crucial for space applications, but also relevant near nuclear facilities or even at high altitudes for avionics. This is an atomic-level assault.
What types of radiation are we talking about?
Ionizing radiation, charged particles like alpha particles, beta particles, electrons, protons, energies typically above 10 keV. Also neutral particles, especially neutrons, which are highly penetrating. They're like microscopic bullets firing through the semiconductor material.
Where does it come from?
Various sources. Cosmic rays, constant high-energy particles from deep space. Solar radiation, mainly protons, but the flux can increase massively during solar flares, which follow roughly 10-year cycles. Earth's Van Allen belts tracked electrons and protons that give satellites a hefty dose over time, like 50,000 to 200,000 rads over 5 years in geostationary orbit. And nuclear installations or events on Earth.
Rads, that's a measure of absorbed dose.
Yes, absorbed energy per unit mass. And these doses can cause significant damage.
So what does this radiation actually do to the semiconductors? The silicon?
Two main categories of effects.
Yeah.
First, ionization. The radiation passes through, knocking electrons loose, creating electron hole pairs, extra charge carriers. This can dramatically increase conductivity temporarily.
Moving to.
Huge ionization currents, potentially amps. This can mess up voltage levels, cause overheating, even lead to thermal breakdown. It's a sudden electrical disruption.
And the second effect?
More permanent damage. Radiation defects or displacement damage. High-energy particles can literally knock atoms out of their proper place in the crystal lattice. This creates vacancies, empty spots, and interstitials, atoms stuck between lattice sites.
Like potholes in the crystal structure.
Exactly. And these simple defects can combine with impurities or other defects to form more complex, stable flaws. The source names specific ones like A centers, E centers, D vacancies. These permanently alter the semiconductor's electrical properties.
So these atomic changes have big consequences for how devices work.
Huge consequences. For diodes, leakage current increases, forward voltage drop increases, breakdown voltage decreases. For bipolar transistors, the current gain, HFE or beta, degrades significantly. They become less effective amplifiers.
What about MOS transistors, the basis of most modern ICs?
They are particularly sensitive to total dose effects. Ionization creates trapped positive charge in the oxide layer, the insulator under the gate. This shifts the threshold voltage needed to turn the transistor on or off.
So the switching points change.
Yes. And transconductance, how well the gate controls current, decreases. For digital ICs, this means the 0 and 1 voltage levels shift, making operation unstable and reducing noise immunity. The chip gets progressively worse at distinguishing logic levels until it fails.
Is some tech better than others? Radiation hardness.
Yes, definitely. The source mentions bipolar ICs might tolerate neutron fluxes around 5 by 1017 per square meter, while some MOS tech might go higher, maybe 1019. Certain logic families like TTLSH and especially ECL, emitter-coupled logic, are noted as being relatively radiation resistant among bipolar types. Analog ICs, however, are often very sensitive. Engineers have to select components specifically hardened for the expected radiation environment.
You mentioned total dose effects being bad for MOS. What about sudden high-intensity radiation?
That can trigger catastrophic failure modes. The most dramatic is latch-up.
Latch-up. Sounds bad.
It is. It mainly affects CMOS ICs, but also some bipolar ones. High radiation rates or electrical transients can trigger a parasitic four-layer structure, like a tiny hidden thyristor, PNPN, or NPNP within the IC.
And what does that do?
It turns this parasitic structure on, creating a low-resistance path directly from the power supply to ground. It's like throwing a switch that shorts the chen internally.
The permanent short.
It stays latched in that state, drawing massive current until either the power is completely removed and reapplied, if you're lucky, or the chip overheats and destroys itself, which is common.
Can you prevent it?
Certain manufacturing techniques help, like using dielectric isolation instead of junction isolation. Rigorous testing and selection radiation culling can weed out susceptible parts, and some technologies, like ECL, are inherently highly resistant to latch-up due to their internal structure and operating principles. It's a major failure mode that designers of space or military electronics work very hard to avoid.
Okay, we've gone through the intense design process for these incredibly resilient systems. But how do they actually get made? Turning those complex blueprints into reliable hardware must be another huge challenge.
Absolutely. The design is only half the battle. The source touches on the world of production technology and quality control, which is just as critical.
It mentions different types of technological processes, TPS.
Right, based on detail and volume. There's a preliminary project stage process, then a detailed working project used for actual manufacturing. Processes can also be single, tailored for one specific product, or typical, like a standard process for making all types of multi-layer PCBs. It's about standardizing where possible for efficiency and consistency.
What are the general steps in making electronics?
Material preparation first, then assembly placing components, soldering, then adjustment or calibration, and finally control testing and inspection.
Automation must play a big role.
Especially in mass production, yes. The source mentioned automated machines for sorting components, cutting and forming leads, applying flux, soldering, like wave soldering or reflow ovens, and washing the assembled boards to remove residues. Sometimes these are all linked in one automated line.
What about the physical structures, the frames, the enclosures?
For manufacturing the basic bearing structures, often from sheet metal, the source mentions specialized tech. Powerful hydraulic presses, often with numerical control, CNC, like an Amada press mentioned, precisely bending and punching the metal parts according to the design software. It's precision metalworking meets digital control.
And there's an assembly scheme.
Yeah, that's important. It's a visual chart that reflects the modular design. It shows which subassemblies, like different RIM 1 boards, can be built and tested in parallel before final assembly. It streamlines the whole production flow.
Which brings us to quality. How is that defined and measured?
Quality is defined broadly as the set of properties that meet customer, state, or global standards. It covers a lot. Does it fulfill its purpose? Is it reliable, durable? Is it manufacturable? Can it be built consistently and economically? What about accuracy, ergonomics, even environmental impact? It's a holistic view of goodness.
Let's focus on accuracy. That sounds critical for electronics.
It is. Accuracy is how closely a manufactured parameter like the resistance of a resistor, the width of a PCB trace, the position of a hole matches its specified nominal value. This is controlled by tolerances, the acceptable range of deviation. If parts are out of tolerance, they might not fit or the circuit might not perform correctly.
How do they check quality during production?
Various methods. The Deming cycle, Plan, Do, Check, Act, provides the continuous improvement framework, but specific techniques are used. Non-destructive testing is key because you want to inspect without damaging the product.
Like X-rays.
Exactly. The source highlights X-ray inspection. It's invaluable for finding hidden defects you just can't see, otherwise breaks inside cables, poor solder joints under components like BGAs, misaligned layers in a multi-layer PCB, voids in castings. It gives you crucial... Very important for process control. Using tools like control charts or dot diagrams, manufacturers track key parameters over time. They can see if the process is stable or if it's drifting towards the tolerance limits. This allows them to make adjustments before they start producing defective parts. It's proactive quality management.
Now, this leads to something that sounds really advanced. Robustness, analysis, and synthesis. What's that about? Ensuring resilience against randomness.
Sort of, yes. It's about designing for inherent resilience against unpredictable variations, especially in very complex systems. The source explains that traditional statistical models can struggle with what it calls large chaotic systems, or LCS.
Like a modern microprocessor with billions of transistors.
Precisely. These systems are incredibly sensitive to tiny manufacturing variations or external factors. Their behavior can become almost chaotic and hard to predict using simple models. A tiny flaw can have disproportionately large effects.
So how do engineers deal with that chaos?
The source suggests using tools from information theory. Concepts like entropy, a measure of disorder or uncertainty, or Kullback-Leibler divergence, a way to measure the distance between different statistical distributions.
How does that help?
It allows engineers to mathematically quantify the amount of information or order in manufacturing data, or the difference between expected and actual performance distributions. It helps identify subtle patterns or deviations that might signal potential robustness issues, even if parameters are technically within tolerance. It's like looking for the signal within the noise.
And the goal is to synthesize a better structure.
Yes, to design an optimal microelectronic structure that is inherently less sensitive to these variations. This might involve defining a mathematical operator that links random variations to performance estimates, and then optimizing the design to minimize the average risk, considering both manufacturing cost and operational performance using a penalty function. It's highly mathematical optimization.
Does this apply to monitoring devices too?
Yes, the idea extends to field monitoring. Instead of just tracking average performance across many devices, the trend is towards monitoring the individual operational area of each specific device. This allows for more accurate error prediction and preventative maintenance tailored to that single unit,
The source also mentioned group manufacturing methods.
like matching and tracing effects. This is where components manufactured very close together on the same silicon wafer tend to have highly correlated parameters due to shared processing variations. Designers can leverage this, placing critical match components, like in differential pairs, right next to each other, ensures they behave very similarly, canceling out some of the random variation and leading to more predictable, robust performance. It's cleverly exploiting the inherent patterns in manufacturing variations.
Okay, we've got the design, the build, the testing, the quality control, but there's one more layer, right? Adapting the system for where it's going to live and work. Designing for a submarine must be different from designing for a satellite, or even just a car.
Absolutely. The intended placement and operating conditions define the class and group of the RES, as the source puts it. This dictates so many design choices, materials, thermal strategy, vibration isolation, sealing level. Everything is tailored to the mission environment.
And different environments mean different kinds of abuse, especially vibration.
Definitely. The source shows data comparing vibration characteristics for different transport types: marine, railway, automobile, aviation. Each has unique frequency ranges and amplitude peaks that the equipment must survive. A ship's low-frequency rumble is very different from a jet's high-frequency vibration.
Let's look at some examples. Naval systems, ships, submarines.
For naval RES, vibrations come from propellers, engines, wave impacts. The source notes how it varies. A large cruiser's stern might vibrate from 0 to 25 hertz with big amplitudes, while a fast patrol boat's rear could hit 150 hertz. Big difference. And beyond vibration, the marine environment demands extreme corrosion resistance, mold resistance, remember the mold, and robust protection against water ingress, splashes, salt spray. It's a wet, salty, shaky place.
What about land-based systems?
Similar factors, but maybe different priorities. Less salt corrosion concern than on a ship. Perhaps more dust or different shock profiles depending on whether it's fixed or mobile.
And the really extreme one, aerospace. Satellites, spacecraft, rockets.
These face the toughest combination of conditions. Their job is critical motion control, orientation, stabilization, navigation. They have to work.
But getting them there is brutal.
Incredibly brutal. During launch, acoustic noise can hit 150 dBs near the engines. That's physically damaging sound pressure. Accelerations, as we said, up to 15 G for big liquid rockets, but a staggering 50 gram for some small solid fuel rockets.
50 times gravity.
Components are literally trying to tear themselves off the boards.
Yeah.
Plus, you have the rapid drop in atmospheric pressure from normal to near vacuum for unsealed parts. And wild temperature swings. Surviving launch is often the single most demanding phase for the electronics.
Even our everyday portable devices have requirements, right? Though less severe.
Yes, portable RES. They're typically designed around the human comfort zone. Roughly 1824 degrees C, moderate noise, 70 to 85 dB peace, typical humidity, 20 to 90%, up to maybe 3,000 meters altitude.
But what if conditions beyond that?
Here's the interesting part. The source points out that humans can only survive for minutes outside that comfort zone. ADG below -17 degrees C, above plus 43.5 degrees C, 120 dB noise, very low humidity, high altitude. But the electronics often need to function or at least survive those harsher conditions, even if the human operator can't be there. Your laptop might be rated to operate down to 0 degrees C, even if you wouldn't want to use it there.
So the device has to be tougher than the user in some ways.
In many cases, yes. Ultimately, every single design choice, from the tiniest REN 0 component to the overall REM 3 assembly, is tailored. It's optimized to ensure the system performs its function reliably within its specific, often incredibly demanding operational context. It's engineering purpose-built for survival. Hashtag tag tag outro.
Wow. This deep dive has really truly pulled back the curtain on the incredible and usually completely unseen engineering that makes our electronic world actually work.
It's layers upon layers of complexity.
From battling fungus in the humid tropics to surviving the sheer crushing force of a rocket launch. Every device, whether it's in your car or orbiting the planet, is just this testament to meticulous, intelligent design.
And it really highlights that continuous struggle against uncertainty, doesn't it? Whether it's the inherent randomness of component failure or the unpredictable effects of a solar flare hitting a satellite. That constant quest for robustness through smart structures, advanced materials, rigorous testing, precise manufacturing. It never really ends.
It's fascinating. So the next time you pick up your phone or see a weather satellite image or even just start your car, maybe take a second to consider the invisible battle that device is designed to win, the heat, the vibration, the potential interference,
Yeah.
the sheer ingenuity packed inside. It really makes you think about how human innovation is constantly pushing the limits, doesn't it?
It absolutely does.
Hmm.
And it makes you wonder, what other unseen forces, what other invisible battlefields might be shaping the technology all around us right now that we don't even consciously consider? That's something for you to mull over.